Hello and welcome to Chandler Science, AB Physics 1, Describing Motion, Part 2. In today's lesson, we're going to look at the differences between distance and displacement, speed and velocity, and then at the end of the video, we'll take everything we've learned so far and we'll do some actual physics problems together. Alright? If you're one of my students, don't forget to take your notes and write down 3 questions or clarifications to ask about later on in class. If you are from somewhere else on the internet, welcome and I hope you enjoy. Alright, with that said, let's go ahead and get started. Alright everyone, well, in order to describe motion accurately and make predictions about where objects will be in space over time as they move through space, that's what motion is, right? We got to have some terminology to help us define how far things have traveled. So distance and displacement. You've already probably know what the term distance is, you use it all the time, but you might not know what displacement is, so let's be more specific in these terms and define them. Alright, so distance is the total amount of ground or air or water that you travel through on a journey, right? So let's say you start at your house, you go across the street to the gas station, and you go to the movies with friends across town, and you come home. Your distance would be every leg of that journey added up, right? So maybe it's 20 miles or however long it is, right? You add everything you did up. But displacement is different, and this is where students can get a little confused. Displacement is the straight line distance from your initial position, wherever you started at, to your final position, wherever you ended at. And displacement doesn't really care about what you did in between, right? Doesn't care. Now, in AB Physics 1, we're really only going to focus on displacement. We don't really care so much about distance. It comes up every now and then, but very rarely. So we're really going to dive a little deeper here on displacement. All right, so let's go ahead and do that now. All right, so we're going to use displacement to solve a problem or, write it down in a formula. We got to have a symbol for displacement. We don't write the word displacement out. That'd be pretty annoying. So our symbol for displacement, and here we go. There's some first real physics stuff here, is delta x. Now, hopefully you remember from your math or geometry class this term delta. It's called delta, not triangle, right? So what is this triangle symbol, delta? It means change in, okay? Change in. Okay. Well, change in what? Well, change in x, because that's the next thing that follows it, right? So change in x. Well, what is x? You might think, oh, well, maybe x is displacement. And actually, x is position. Remember we said before, what displacement is that it's the straight line distance from your starting initial position to your final position, right? So what displacement actually is a change in position. So we use delta x, right? Now, delta x, so change in position. All right, so what does that mean though? How can we kind of flush this out and describe, be more descriptive? Yes, we can. So let's get a real formula here. So that's a symbol for displacement. Now, anytime in physics, now this is our first example of this, but anytime in physics where we have this triangle, and we have a lot more of these triangles, delta, I shouldn't say triangle, delta, this delta stuff. Anytime you see that, it always means, every time, without exception, final minus initial. Final minus initial. All right, so what do we say here? We say, okay, well then we have a final position minus the initial position. Now I'm going to use a little f for final, the subscript f, and the subscript I for initial. So they're both positions, right? They're both x, they're both positions, but it's different times, right? At one time I have my final position, and another time I have my initial position. So I want you to like tattoo that on your forearm or whatever you got to do to remember. But anytime you see the delta, whatever, in this case delta x, it's always final minus initial. Okay. So for example, let's say we are on a number line grid, kind of like our motion diagrams before. All right, and here's our say 0 is here, and then every mark is like a meter. Okay. And so we start at our initial position here of 0, and we go 2 meters forward. Exciting. Okay, and we end up here. All right, so this is our initial position. I'll put an I there. I'll put an F here for final. So with our displacement now, obviously, if you all know it's 2, right? But here's I'm illustrating a point. That our final position was 2, so positive 2 is here, minus the initial where we start at 0. So what is 2 minus 0? Well, obviously you know it's 2, right? But you get the idea here. Okay, see it's 2, and then we'll say it's meters. Okay. So it's always final minus initial, and you see how that works out, right? So some of the stuff about displacement, we got a symbol, we got a formula. What are the units? Well, the SI, or standard units for displacement, is the meter. Okay, now you might also get measurements in kilometers or miles or light years or all kinds of crazy stuff. And in general, you want to convert those things to meters if it's not too hard. Each question might be different, but most of the time we're going to use it, keep it in meters. But you can get other crazy units too. And then the last thing is, let's see here. Is displacement a scalar or a vector quantity? Turns out it is a vector, which means it has direction, right? So let's look at our quick little example here on the number line, our motion diagram. If we started here and ended there, what direction we go? We went that way, right? Or we could say in the positive direction. In one-dimensional motion, we only have 2 directions. We have forward or positive, and we have backwards or negative, right? So in this case, we could say this is in the positive direction. That's kind of the standard, right? To right is positive and left is negative. Up is positive and down is negative, and forward is positive and back is negative. That's the standard. You can change those, but be careful. The default is that, okay? So let's do one more. It's a little bit weirder, maybe. Let's try this. Let's have another line here, and then let's say, all right, what if I put the 0 here this time, and I have 1, and this is 2, and this is 3, and we'll have negatives going this way. All right, let's say we start at, let's say we don't start at 0. Okay, let's say we start at the 2. I don't know, why not? And let's say we end up at the, let's say we go to the -3, and we stop for a minute, but then we come to the -1, and we end there. So this is our final. So it's initial, an I there, and an F for final. Okay, now let's use our formula to find out what our displacement was, our delta x. Our final position looks like it's -1, right? Now remember, the negative sign doesn't mean that we went backwards in space or anything like that. It's just a position, like a grid, right? Like a table, like a graph. And then minus a +2, all right? So we have -1 minus 2. All right, so what was our displacement? X is -3 meters. -3, it's weird. So it can't be negative, it turns out. What does that mean? Well, look at the direction we went. We started here, right? We ended there. So what direction we go? We went to the left, right? We just said that positive is forward, so right, but left is usually considered to be negative. So in this case, we went to the negative direction, those 3 meters, right? And only 3 because we stopped here. Okay. So let's look at the one more thing I want to mention to you. And this is this top example again. We started here and ended here. In this example, this first one up here, is my distance the same or different as my displacement? It's the same, right? In this case, it is the same. But in this bottom example, however, is my distance or displacement the same or different? So in this example, it turns out it's different because I started here, I went this far, and then I came back a little bit, right? So what was it? My distance in this bottom example was, let's see, 1, 2, 3, 4, 5, 6, 7, actually 7 meters would be my distance in this example, right? Because I went really far and then I came back. So it turns out anytime that you don't go in a straight line, your distance is always going to be greater than your displacement, right? But if you do go in a simple straight line, point A to point B and stop, your displacement and distance will be the same. However, your displacement can never be greater than your distance, all right? Maybe if you travel through like a wormhole, but let's not get into that, okay? That's too weird. All right, so displacement can never be greater than your distance, and they can be the same if you go in a straight line. So there's 2 examples that we saw from going point A to point B, going 2 positive meters forward, and there's one where we kind of changed it up. What about this example? All right. Well, so what was my displacement and what was my distance and my little journey there? Well, my displacement was 0, right? I am back in my chair where I started. I didn't go anywhere, so my displacement is 0. If it is 0, you don't have direction on 0. You can't say 0 meters north or 0 meters to the left, right? It doesn't have direction. So it's just 0. But my distance, however, will be a lot more, right? I didn't measure it, but probably a couple hundred meters. I ran all over my apartment complex, so... But, you know, distance, whatever, don't care so much about that. So displacement can be 0 if you end up back where you started, and this distance is really never 0 unless you just don't go anywhere, right? All right, so I hope that the distinction is clear between displacement and distance. Let's move on now to velocity and speed. All right, so we talked about displacement and distance, and that's how far we go through space, but velocity and speed tells us how fast we're moving through space, which is just as important, if not more so. So let's discuss velocity and speed and the difference between these 2 terms. Now, you're probably familiar with the term speed. You're probably familiar with both, but you're probably more familiar with speed. You probably use that term a lot. So speed is determined by using distance, right? So speed is, I'll write a little formula down here for you. Speed, and we're going to call it S, is the change of your distance divided by your time, okay? And remember we said before that we don't really use distance that much in AP Physics 1. It's mostly about displacement. So speed tells you how fast you're going, right? I am going, remember from our last video, we talked about the motion maps, and we were going, you know, maybe we're going 5 meters per second, right? So your position is changing by 5 meters every second. That's an example for speed, right? The typical units are meters per second. That's our standard units, but they could be different. It could be kilometers per hour, or they could be miles a minute, or who knows, right? Just depends on the problem. But standard, we want to try to keep it in meters per second most of the time. Okay, so that's speed. It's useful sometimes, but to be honest, not that often. Let's talk more about velocity. That's much more important. All right, so velocity is determined by using displacement. Okay, so now give the formula in a minute. We almost always want to use velocity in this class, really never talking about speed. And the reason that velocity is better, as we mentioned before, it is a vector, right? I mentioned it as an example of a vector before. That means it has direction. So velocity is like speed with a little extra. So you got velocity, tells you how fast you're going, and in what direction you're going. This is super important. Velocity is one of those 3 or 4 most important quantities that we're going to measure and talk about all year long. So you've got to understand what velocity is, what it means, and be able to discuss it, right? So let's talk more about velocity since it's so important. All right, so the symbol for velocity is going to be a simple V, like that. And for velocity, let's get a formula for it. We already know that velocity tells us that it's how fast we're going, right? How much space we move through per unit of time. So it might be able to even kind of surmise on your own what the formula might be. We said we use displacement for it, so it's got to be displacement in the formula somewhere. So there it is, delta x over or divided by time, right? And I'm going to put delta in front of it just too. So the change in time. So the change in position divided by the change in time. Okay, so let's do some examples just so you know what I mean. Let's say that here we are at this position right here, and then there's a position down here that we want to get to, and let's say this distance is from there to there. It is, I don't know, 10 meters. Okay, and we start our journey. Let me go. I try to do a straight line, but me and straight lines don't get along so well. So there's a straight line path to the other spot. Let's say it took us, I don't know, how about 10 seconds? Okay, well then our change of position, if this initial position was here and our final position was there, a straight line distance, remember we said that before, that displacement is a straight line distance from initial to final position. We said it's 10 meters, so our displacement is 10, took 10 seconds. 10 over 10 is of course 1. So our velocity is going to be 1 meter per second. So we are traveling at a speed of 1 meter every second. Every 1 second, we go 1 meter, right? All right, so pretty simple stuff. Again, the units need to be in meters per second most of the time, unless the problem says otherwise, but try to keep it meters per second. Let's see, it is a vector, as I mentioned. It has direction. And if we ever get a negative velocity, all that means is that it's going the other direction, right? It doesn't mean that it's like you're moving backwards through space-time or something crazy, right? The negative sign doesn't mean some crazy thing. All it means is, oh, different direction. For example, if this here was in the positive direction, and let's say we decided to go back. We got to our final position, we had a picnic or whatever the heck we were doing, and we go back to the initial position. Well, on the way back, on a return journey, this way, we would have a negative velocity, right? Because they're going in the negative direction, okay? So all the negative sign means is direction, all right? Now I want to say a quick thing about time real quick. I notice I have a delta t here as well. So let's say you start a race, okay? When fire the gun right to start a race, like the starting pistol, all right, that's usually considered time is 0, right? So our initial time is usually 0. It's not always 0 though, right? But most of the time it will be. So whenever you're measuring an event, okay, whether it's a race or, a planet going around the star, or it doesn't matter what it is, any event where an object is moving through space, usually the initial time is 0 because you kind of decide, oh, I'm going to start my timer right now, right? That's the 0 time. But it's not always 0, so just be careful. Now, the final time, TF, is however long the event lasts, okay? However long it takes you to go from this initial position here to the final position there. Or however long it takes the planet to go around the star. Or whatever the thing is that you're measuring, it's how long the thing takes to happen, right? And you decide how long that is, right? If you want to stop the stopwatch, so to speak, at any point, you can, okay? So the final time is how long it takes for the thing to last, okay? So from the initial moment, you start the stopwatch, and the time final is when you stop the stopwatch, right? Is when you stop your measuring. Okay, so in this case, it was 10 seconds. Okay, so that's what we had at 10 here because it's change in time. Remember, change in always means final, so it'll be TF minus T initial, right? So TF was 10 minus 0, of course, it's 10 seconds. So that's why we had 10 as our change in time, all right? So time we measure in intervals. We don't just pick a random time, right? Like you don't. Okay, if I said to you, "What's the time right now?" You said, "Oh, it's 3:30 p.m." Okay, cool, it's 3:30. But that's not an elapsed time, right? Well, you can't measure anything in a single moment of time. You need time to elapse. Okay, so that's what change in time means, right? It's a measurement of the evolution of time. Okay, all right. So that's velocity and speed. Let's go on and now and try to do some real physics problems. All right, here we go. We're going to do 3 problems real quick. Shouldn't take too long. In my class, every teacher has different little methods that they teach their students on kind of how to set up problems and solve them, right? And I've adopted what is known as the GUESS method. All right, so it's an acronym. It doesn't mean just screw, just guess. That's not what it means. It's an acronym. It has actual meaning. Okay, although some of my students want to just say, oh, you said to use the GUESS method. All right, so what's the G for? G stands for givens. U is unknowns. The E is equation or expression. The first S is substitute, I'll just write sub, and then the final S is solve. All right, so this is kind of gives you the order of things that you want to try to do to solve pretty much any problem. Okay, first thing is givens. What does the problem give us? What do we know for sure? What is given to us? All right, let's read the problem. Daniel walks from his house to the corner store at a constant velocity, which is 3 kilometers away to the south in 24 minutes. What was Daniel's average velocity during his walk? All right, what does the problem give us right off the bat? Well, it tells us that from his house to the corner store, it is 3 kilometers to the south. So we know that delta x is 3 kilometers to the south. All right, so I'm going to write that down. Let's see, what else does it tell us? What does it give us? It says time. It says the time it takes Daniel to do this is 24 minutes. Unknowns. What is it looking for? What is it asking us to solve for? What's the unknown thing? In this case, it's velocity. It wants to know that. I'll just put a little question mark to symbolize, hey, we got to find this thing. What's the equation we're going to use? Wow, maybe the one we just learned, right? It's going to be velocity equals displacement over time. Okay, and then substitute. We're going to plug numbers in, and then we're going to solve. But before we do that, we got a problem. I want my answers in meters per second for velocity, right? Unless otherwise stated. Okay, if I say in the problem, you can, it's okay to leave your answers in this. If it doesn't say that, then you need to have answers in meters per second, the standard units. All right, so we got to do that then. All right, we're on kilometers a minute, so we got to convert from kilometers to meters and from minutes to seconds. Okay, not too hard though. Let's do a little dimensional analysis here. So we have 3 kilometers. In case you forgot how to do dimensional analysis, a little quick review. So write down your original units that you have. You start with kilometers in this case. I have 3 of them. Now I want to cancel kilometers and convert to meters. All right, so if I have kilometers up top, I want to put kilometers on the bottom. It's just like you divide things, right? The top and bottom things can cancel. They're the same, they cancel, right? So kilometers are going to cancel here. Now, there are 1,000 meters in 1 kilometer. So I'm going to write 1 kilometer and then 1,000 meters up top because these things are equal, right? 1,000 kilometers is 1 kilometer. So it's like saying we're multiplied by 1 in a sense, right? So kilometers cancel though. This kilometer goes away, kilometer goes away. Now look, I'm in meters. Yay, meters. Okay, so 3 times 1,000. See, everything on the top of the little bar, you multiply across the top. And any number on the bottom, you divide by it. So 3 times 1,000 is 3,000. And then divide by the numbers on the bottom. So divide by 1. But divide by 1 is just the same thing, right? So it's just 3,000. So 3,000 meters. There we go. And it's the same thing for time. All right, 24 minutes. I'm going to start off with my initial number value in minutes here. Draw my little crossbar there. I want to have minutes on the bottom because I want to cancel minutes. And then I want to convert to seconds. All right, so write the units up top. Well, in 1 minute, there are 60 seconds. It's an easy conversion. So now look, minutes cancel, and now I'm in seconds. 24 times 60 is 1,440 seconds. Now we have the right units. Yes. Okay, now we plug it in. Now we do the substitution. This is my displacement, right? 3 kilometers to the south. That's how far we traveled from our initial spot to the final spot. So plug this number in to the x, and then plug this number in to the t. So we're going to get velocity equals 3,000 over 1,440. And that's going to equal for us 2.1. And I'm rounding here to the 1 decimal place is fine. 1 or 2 is really fine. Not really worried about that so much. All right, 2.1 meters per second. What direction? It did say it went velocity. Velocity is a vector and has direction. He said it went to the south, so we're going to write S for south. Or we could draw an arrow down to represent south. Also, that's fine. Okay, there we go. 2.1 meters per second. Very good. Let's do another one. Maria is swimming in laps in a pool. Okay. The pool is 50 meters long. Cool. Maria swims 6 laps in 2 minutes. That is really fast. What is her average velocity? What is her average speed? Okay. Maria swims 6 laps in a pool. All right, now a lap in a pool is down. Not down and back. I looked this up. I Googled it. Don't argue with me on this. I Googled it. You can Google it too. I had to because I wasn't sure. I was like, wait a minute, is a lap down and back? Okay, so in swimming, a lap is just down. Not down and back, just down. All right, so here we go. What are our givens? What do we know for sure? Well, it takes her 2 minutes. We know that for sure. Time is 2 minutes. We're going to have to convert to seconds probably, huh? Because we don't like minutes. Let's see. And the pool is 50 meters long, but she does 6 laps. So if the pool is 50 meters, let's draw a little picture. 50-meter long pool from one end to the other. And she does it 6 times. Okay, so she does it 6 times. And she can start here and it goes down. That's 1, 2, 3, 4, 5, 6. She's going to end up in the same spot she started from. So what does that mean her displacement is? Displacement, if her initial and final position are the same spot, her displacement is 0. She has no displacement. What's her distance though? How far does she go? How does she actually travel, right? Well, she actually went, let's see, 56 times, right? So that's 300 meters. So she actually traveled the total distance 300 meters, but her displacement was 0, right? All right, we have time, we have distance and displacement. Looking for velocity. I want to find the velocity of my unknown, and I want to find speed in this one. So 2 unknowns here, no problem. Equation, same thing as before. Our velocity equals displacement over time. Or this is pretty easy. Our displacement was 0. So 0 divided by anything, whether it's minutes or seconds, doesn't really matter, right? Because 0 divided by anything is 0. So we had no velocity. So man, her coach should be like, God, Maria, you're so slow. Your velocity was 0. You slacker. All right, that's what I would do if I was a coach, but I'm not a coach. Okay, anyway, all right, so velocity 0. What about speed, though? Okay, speed's a little different. Speed, we said before, was distance over time. And it does need to be in meters per second also, so I want to convert the time into seconds. So 2 minutes, and convert this to seconds. So at 1 minute on the bottom, that's 60 seconds in a minute. Minutes cancel. 2 times 60 is 120. Divided by 1 is just still 120. So I have her distance of 300 meters over our total time. It's a 3, sorry. My handwriting is not great. Over her time, which is, we say 120 seconds. So her speed is going to be 300 over 120, which is 2.5 meters per second. No direction here because speed is scalar. It doesn't have direction. It's just a number. It's a value. That's it. Magnitude only. All right, so that's actually like record-breaking speed. So congrats, Maria. You actually are really fast. I googled this earlier. Also, the fastest swim speed ever recorded for a human is like 2.4 meters per second. So Maria, you're doing awesome. Keep it up. All right, so there's our velocity 0, speed at 25 meters per second. Okay, so they can be different too, right? All right, I'll do one more problem here. And this time we got George. George is doing a little run, going for a run. George runs 2 kilometers at a speed of 12 meters per second. How long did it take George to run the distance? Ooh, okay, so this time we're switching up a little bit. It gives us the displacement here. It's 2 kilometers, so let's assume he runs in a straight line, 2 kilometers. It gives us velocity at 12 meters per second. That's pretty fast. And then it says, how long did it take? So this time our unknown is our time. We're looking for t. What equation we're going to use? The same one as before. We're just going to rearrange it a little bit. All right? Rearrange it a little bit. This is, now we're getting the territory of students tend to, oh my God, I got to rearrange letters in a formula. Yes, you do. Get over it. All right. All right. Now I'm going to recommend, before we go to the first S and substitute in, I am going to say, and for my students, this is mandatory. If you're from the internet, you can do whatever you want, but I suggest, highly suggest, that you move the letters and stuff around before you start plugging in numbers. Trust me on this, it's going to save you time and eraser marks and points on a test probably, okay? The reason why you want to move letters around first is because letters are easier, believe it or not, than moving around big old fat numbers, okay? So what do you mean, Chandler, move it around? Well, what I mean is, if I'm solving for t here, right, the unknown is a t, so I want to solve for my delta t. But it's in the denominator on, of this fraction. That's kind of annoying. So what I want to do, anytime I'm solving for a variable, I want to get that variable alone on one side of the equal sign by itself. Like the v in this case, right? The v is all by itself on one side of the equal sign, so it's like v equals this thing. But the t is not by itself, and it's also in the denominator, which is a pain in the ass. So we want to get that t by itself for whatever variable we're trying to solve for. We want to get it by itself on one side of the equal sign alone, okay? So how do we get t on one side of the equal sign? I don't care which side, either side, by itself. First, we're going to multiply by delta t, both sides of my equation, right? Whatever I do to one side, I must do it to the other side. So these delta t's cancel, right? Because you got one on top, one upstairs, downstairs, they cancel out. But now look on the left-hand side, we have delta t times v equals delta x. But now we can divide by v both sides. Now these v's cancel, so now I have delta t equals delta x over v. Now we have delta t all by itself on one side of the equal sign. Cool. Now we can plug in numbers. All right. Now it's safe to plug in numbers. All right. So what was our displacement? Oh, we're in kilometers again. I want to be in meters. So let's convert this. You probably have, hopefully, get the hang of this conversion thing by now. So, all right, kilometers here and here. So they cancel. 2 times 1,000 is 2,000. Divided by 1 is still 2,000. So 2,000 meters. My delta t over my velocity, which the problem told us was 12. So how long does this take us? George, it took you 166.7 seconds to run 2 kilometers. That's like over 2 minutes, just over 2 minutes. That's what, 2.5, almost 3 minutes. So that's pretty fast. So George, you're awesome. Keep up the good work. Speed demon. Okay, there you go. There's our answer for how long it took George to run the 2 kilometers. Hope you learned something and got some good practice in there. All right, guys, remember, hope you have, if you're my students, you have your notes, 3 questions or clarifications for later on in class. Hope you enjoyed the video. Don't forget, leave a comment down below if you have a question, or you can message me on Remind. Email me at any time. I have no life. You are my life. So message me with questions anytime, day or night, and I will respond to you. Well, with that being said, thank you for watching. See you later.